As was said, I did a master's in space science, but during that time, I mean, you know, I had visions as a kid of being an astronaut and things like this. But then growing older, I got interested in propulsion systems and got to a point in my degree where I was starting finding more of the bigger kind of sciences, such as astrophysics and particle physics, more interesting. And really, it was the influence of a couple of professors on the summer school I went to. They kind of told me about neutrino physics, and it was really an emerging subject. I mean, this character change between different types of neutrino was only measured for the first time in 1998. It wasn't until 2001 that we had actually seen the third and final type of neutrino in nature. So neutrino physics is still very much emerging field, even though a lot of the maths and theoretical framework's still there. Experimentally, it's again, you know, quite flourishing, and that kind of, you know, provided challenges and just kind of drew me in, and I guess I was more interested in the challenges than anything else.
Off the back of that question, how do you know there's only 3?
We know that there's only 3 that interact via the weak force, and the reason for this is you can tell by the different ways in which these weak force force carriers die. Essentially, you look at their death cycles, and they all die into the 3 different types of neutrino and or the 3 different types of charged electron or heavier. And you can measure the number of degrees of freedom into which they can die, essentially. This was measured to very high accuracy in the predecessor to the Large Hadron Collider in different experiments separately to obviously produce, you know, that duplication that you need. And it was measured to a massively higher degree that there are only 3 degrees of freedom, essentially, for these to die into. So. But there may be ones that don't interact via the weak force, and that's another question. There might be.
Completely invisible.
Completely invisible, yeah, so why would we be interested? But yeah, they could exist. So. Yes, sir.
Sorry, are there any theories that predict neutrinos? Sorry, different types of neutrinos other than the 3 that have been discovered so far? Because I know, like before, the Higgs boson was theoretically proposed 70 years ago, 80 years ago, and only now have we been trying to experiment, trying to actually find it. So, are there any like theories that, or mathematical formulae that try and predict neutrinos, or any different types of neutrinos?
So we can look for different types of neutrino that don't interact via the weak force by looking at the character change again. Because this oscillatory probability change of what type of neutrino you might see at a certain distance for a certain energy, you measure the numbers of this oscillatory pattern, how often it peaks and troughs, and how often it changes. And you can measure these numbers, and you would only expect to, if you have 3 different types of neutrino, you'd only expect to be able to, you'd only need 2 or 3 numbers to perfectly define this oscillatory pattern. But if you see something that's inconsistent, if you measure more modes, if you like, more peaks and troughs than you'd expect, then that can only be associated to maybe a 4th type of neutrino that these things are changing into, but a type of neutrino that we definitely can't see via the weak force because of the things I explained earlier. And so there are searches for these, and they're called sterile neutrinos because they don't interact at all. And all of the experiments, such as the one I'm on, do look for these sterile neutrinos. But we are pretty confident so far. We haven't seen any evidence for them at all.
Oh, this one.
Sorry, it's one more.
Oh, sorry. Just a quick question about if you only find like 1 neutrino a day kind of stuff, I mean, what do you do for the rest of the day? I mean,
Yeah.
What kind of maths do you use, or what is the statistics you use, or are you kind of using calculus, or what is it, numbers, like what exactly is the maths involved in all this? Statistics mostly?
Well, if you like, it's like putting a dot of paint on an impressionist painting a day and waiting to see the picture build up. That's essentially what we have to do. And the rest of the time, I mean, we've got bigger detectors now, and as I say, we've got more intense ways of firing. We actually fire neutrinos, so it's much more intense. So we get to see larger numbers. But the rest of the time, what is also important is that we know exactly how our detector's working and how often we might see something that isn't a neutrino. So we're always constantly measuring, well, in fact, heavy electrons, muons, coming from the sky. We use them to make sure we understand exactly how our detector's working, so that when we do see a neutrino, we know we can calculate its energy and direction accurately. So, yes, sir.
Can I ask a question? Are you disappointed that the term neutrino has been coined, given that you work in the areas of neutrinos?
Neutrino, no. I mean, that's a whole new. So I mentioned symmetries between matter and antimatter. A neutrino is a supersymmetric neutrino, and so there's other. So you've got matter and antimatter, but you've also got a mirror version where you have things called supersymmetric particles, and this is, yeah, I can try and explain it. It's a symmetry between the force carriers and the matter particles, and so they kind of change. There are other properties which they change around. Kind of inherent properties, not to do with the forces themselves. And you can, I mean, you know, you've got neutralino, you've got the tauino, muino, and then you've got squarks. And so that's just the way that they're coined. And supersymmetry has been dealt a blow recently by the LHCb experiment. They've kind of measured a whole vast amount of possibilities for supersymmetric particles to exist, and they've kind of quashed them. There's still areas in which they can exist, and you know, it'd be very interesting to see if that is new physics, because things like supersymmetry kind of gives a common point in the early universe where all the forces were one, where they were a common force, and that's important for, you know, unifying well, everything at a common beginning. So yeah. Sorry, is this okay?
Sort of speculative stuff. This is 2012 now, and this is a big year for the LHC. So, what changes do you foresee for the standard model from results this year? As a gambling person, I mean, obviously it's early in the year.
Yeah, you said already you put some money on the Higgs, so which yeah, it's fair enough. To be honest, I would have put money on it as well, not being found. I like being a bit skeptical. It's a big year for the LHC because they are going to rule out or see the standard model Higgs. With the data they're expecting this year, they will rule out or see whether the standard model Higgs exists. As I say, if they don't see this standard model Higgs, the one that is being used currently in the theoretical framework to give mass to all the particles, then you're going to look to new physics. You're going to look to things like supersymmetry, or, you know, so there are other models as well, other Higgsless models as to how mass could be given to these particles. And so if you don't see the Higgs, I think, again, very exciting, because it means you don't know what you thought you knew about the universe. There's something else beyond that, and then that's brilliant because you start getting to think of new experiments, new ways of kind of trying to see how nature's working. So I think that'd be brilliant. And in terms of neutrino physics, we'll probably get to the point, not the end of 2012, but in 2013, where we start to look at the difference between matter and antimatter, because now we've kind of pinned down the changing characteristics. We can start looking and comparing matter and antimatter. So, yes.
Yeah. So send a message in neutrino. How would it send a message in neutrino?
Because we send them in short, sharp, billionths of second bursts, you send it as a 0 or a 1 in binary. So if you see a neutrino burst, it's a 1. If you don't, it's a 0. And because the timing is accurate enough, you only need to see the 1 neutrino. So you send trillions of these things in very short bursts, and you have a probability that you'll see it. And if you do see it, and that's good, that's a 1. Or if not, it's a 0. That's where they get their 99% accuracy from, seeing 0s and 1s. So.